Welcome back, everybody. Hope you can hear me well, everybody. So the topic today is essentially going to rotate around the solution of this specific homework. Keep in mind that we changed the deadline, so the deadline is not today, and that's simply because, most of you did heroic efforts, so all of you did heroic efforts with the second midterm. And then, since you only had some few days, we thought of postponing the deadline till Wednesday next week, the 28th. No, 28th is actually Thursday. And then during the weekend, you can find an additional homework. This is optional if you want to do it. And then next week, on Friday, we are going to make available the final one. And that counts 30% of the final grade. And it's due by May the 6th. We are going to, for that specific final, we are going to keep the kind of hours which we have today and the office hours as well, the week of finals. So if you have questions about it, you can swing by here, or you can join us via Zoom on the office hours. So that week, in case you want to discuss the final, we will try to keep this kind of hours open for all of you. So if you have questions, things which are unclear, there's always a possibility to come and discuss. Now, I'm going to sneak in 10-15 minutes today on the Lagrangian theory with constraints. And one of the reasons is that the final part of exercise 5 deals with that. We are going to take a top-down approach today. And then on Monday, we are going to derive the mathematics of something which is called Lagrangian multipliers. The bonus with what we are going to do today is that we are going to obtain interesting physics information by just starting with kinetic energy and potential energy. And that's pretty neat. So I'm trying to give you this as a kind of teaser for what is going to come next week. And now I'm just going to set up the type of modified Lagrangian, which we can use with the Euler-Lagrange equations. And with that, we can actually get some interesting physics information. And then on Monday, we are going to go through more the mathematics of this additional part of Lagrangian calculus. And Wednesday next week, we are going to dedicate mainly to examples on how we can use this formalism to physics cases. So let me steal 10 minutes of your life and just try to wrap up what we did on Wednesday. So if we now just switch to the whiteboard very quickly. So on Monday, we looked at what we called Lagrangian calculus or variational calculus, Lagrangian with constraints. And this is a very interesting field, actually. And you will see that it is very, very powerful, and it allows us to derive equations of motions, just starting with kinetic and potential energy and a constraint on the system. I think that's pretty cool, actually. So the system which we looked at on Wednesday was an object which was sliding down an incline. So we had something like this. So we had in the X and the Y direction. We have an angle alpha. And then we have an object which is sliding down. So the constraint here is that of an object which moves on this plane, this inclined plane. And as some of you said on Wednesday, this constraint is something which we can model with tan, the tangent of the angle. So the constraint which we have is now given by y is equal to x times tan alpha. That means that we can define a function of x and y, which is equal to 0, which is simply y minus x times tan alpha. So you can define many such functions. You could think of you moving on the surface of a sphere. In that case, the constraint you would have is that you have to move on the surface of a sphere with a certain radius, right? So in this particular case, what we have defined now is a function which in mathematics is called a holomonic function because it's equal to 0. So this is a constraint which we are now going to model mathematically. So I said, I'm going to take the top-down approach because what happens now is that y and x are no longer independent variables. So just keep that in mind as a kind of keyword for Monday. So when you can express one with the other, then there's only one of the variables which is independent. So the motion here, when you have fixed alpha and x, then you have fixed y, and vice versa. If you fix y and alpha, you know the value of x. So this is a typical solving a problem with a constraint. And with Lagrangian calculus, you can actually do this in a very elegant way. So now I'm taking the top-down approach. So the thing we do, and we will go through the mathematics on Monday, is that we define a new Lagrangian, which is going to look like as follows. So we are going to define a new Lagrangian, which is given by kinetic energy. So we have a 1/2 of m, I have x dot squared plus y dot squared. And then I have my potential energy, which is simply the gravitational field, minus m times g times y. Now, this is my potential energy, right? And then I have an additional term, which is given by, so I'm telling you, I'm just giving you the top-down approach today. And then on Monday, we will derive where this parameter lambda comes from. So I can define a modified function. And with this modified function, I can now apply the Euler-Lagrange equations. And we are going to get an interesting result here. So let's look at how we can proceed now. So we are not setting up the forces. So the typical way we began in the beginning of the semester, we know that there would be a normal force and there's a gravitational force, and there could be friction as well. But let's now assume that there is just a gravitational force and a normal force. So traditionally what you would have done is actually to set up the forces and then find the equations of motion via the acceleration. Now we are starting with potential energy, kinetic energy, and this additional constraint. And we are going to get an expression for the normal force. So let's try to solve the equations. So what we're going to get then, when we use the Euler-Lagrange equations, so these are the equations which we always apply when we want to find the optimal parameters x and y. So we're going to solve it for d dx minus d dt, and then I have an expression with respect to the derivative of x, and this is acting on the Lagrangian, the new Lagrangian which we have, this function here. And this is equal to 0. So if I do the math, what I'm getting is a minus lambda tan alpha. So I'm taking the derivative of this function g, which contains x. And sorry, it's not x. Sorry, I did something wrong here. I'm using x and y. Sorry for that, x and y. So this is a function, this g is a function of x and y. So what I'm getting then is that this becomes minus m times x, second derivative, and this is equal to 0. Then I can do the same thing with y. So if I take d dy minus d dt and d of y dot, and multiply that with L and put that one to 0, what I'm getting then is a new equation which simply runs like this is equal to minus m times y second derivative minus m times g plus this lambda. So this doesn't look like any kind of thing which we can use. So one thing which you can do now is actually to manipulate this equation. So what we are doing now is to take one equation and subtract from the other ones. You can multiply one equation with some function. If you see that there are some functions which are useful, you have a tan alpha here. So a typical trick you would do now is to multiply one of these equations with a function or something, and then you subtract the other one. And then if you're lucky, or if you have some good insight about the mathematics, you can actually extract something which is simpler. So this is a typical trick which you often use in physics to manipulate equations and simplify them. It's not given that you see that immediately. Actually, I saw that in a textbook. So what comes here, I didn't cook it up. That's a textbook which I saw when I was doing a course in mechanics many, many years ago. And then when I was going to present this one, I remember that many, many years ago, I saw something similar. So these are the kind of useful tricks. So what you would do now is the following. So you multiply. So let's label these equations. So I'm going to label this with an asterisk, and I'll label this one with a double one. So we would multiply this equation here with tan alpha, and then subtract the second equation. So remember that both are zero, right? So if I take the first equation and multiply with tan alpha, I would have zero on the other side. So since both are zero, it's a trick which is pretty common to see in both in physics and in solution of mathematical equations. So if I do that, what I get then is the following. I get a minus lambda of tan squared minus m of tan alpha plus m times the second derivative of y plus mg minus lambda is equal to 0. Now this doesn't look like an improvement at all, right? So one thing to keep in mind now is that we have y, which is equal x times tan alpha. This is a constraint which we have. So the angle alpha doesn't change with time. So it means that I could now replace the second derivative of y in here with something which is similar to this. So this is actually equal to the second derivative of x times tan alpha. So we're assuming now that this angle is just locked. The angle doesn't change. The angle of the plane we are sliding down doesn't change. Then, what we get then, if we use this, you see now that the y which we have here can then be replaced with that, and this cancels exactly this term. So this is the lucky circumstance here. So what we get then is minus lambda times tan squared minus lambda minus n times g is equal to 0. Then another thing which we know is that tan alpha plus 1 is the same. This is one of the standard trigonometric relations, is a cosine alpha squared. If I use that, then I can take the equation which we have here, which now contains tan alpha squared plus 1, multiplied with minus lambda. What we get then, if we now remove things to the other side, is that what we have is that lambda becomes then, if I do the algebra, it becomes m times g times cosine squared times alpha. my equation for x becomes equal to minus g times sine alpha times cosine alpha. And then I have a y, second derivative, which becomes minus g times sine alpha squared. Now, this is something which we did back in the beginning of the semester. When we wanted to find the position, we would simply integrate up. First, we got the velocity with an initial velocity at a certain final time. And then we integrated again, and we got the position. So if you do the integration twice here, what you get is actually x of t, which will be equal to x0 plus some initial velocity in the x direction, v0x, times time. And we did this in the very beginning of the semester, so this serves also as a kind of repetition. And then we have t squared times sine alpha multiplied with cosine alpha. And we can do the same with y. There's no need to solve this numerically. These are simple analytical expressions. Sorry, this should be a v0 in the y direction. T minus, and then we have 1/2 g of t squared and sine squared alpha. So we can integrate up. The other thing which is interesting here is that we have an equation here which we can, or we should actually think a little bit about. So take a look at that one. If you look at this one, what kind of dimension does it have? What does it represent? If you take a look at it. From the incline. So what you've done now, by this constraint, you actually get an expression for force, because you see this is m times g. So that means that you have mass times meters or length divided by time squared. And that's the dimension of a force multiplied with a constant. So what you see here is actually the expression you get for this constrained motion. So we started with potential energy, kinetic energy, and a constraint, a mathematical constraint for your motion. And from that, we can actually derive a mathematical expression for the normal force acting on this object. And that's pretty neat. The way we did it in the beginning of the semester was actually to draw all the forces and then solve the equations. Now we are simply using the Lagrangian plus a constraint, and we can find exactly the same type of equations. And that's pretty neat. So that's why the Lagrangian formalism is often so powerful. On Monday, we are going to look at further examples, and you're going to need this one when you solve the last exercise in the weekly assignment here. Any questions so far? I think this is pretty neat. I like this stuff. Okay, so I'm going to stop the recording. Julie is going to answer questions online, whereas I will just move around here, and you guys, you just raise your hands when you have questions, if you have questions. Then I'm just going to stop the recording here.